Thanks very much. It was really great. It's my first time here, and it's really enjoy like master experience. Yeah. So basically, today I want to talk about Seiberg-Witten engineering for family. So in previous lecture, Andreas and Tom, they talked about Seiberg-Witten invariant for single manifold. And today we are going to shift our viewpoint a little bit and think about like the invariants for non-single families. Okay. So let's start by setting up some equation. X in our top will be a smooth manifold. We always assume it's correlated, compact. Sometimes may have we do assume sometimes we allow X to have bound. And main object we are interested in is the diffeomorphism group of X. Then we just consider the group of diffeomorphisms. So this notation will just be mean the diffeomorphism. Orientation to zoning. And we will also require that F equals pi negative nearby. So where X has no boundary at all, we also like we just ignore this solution. That's how like this. And we can equate this with the same topology. This will be a topological form, and we want to understand. Okay, understand. So, yeah. So, well, I mean, studying the homomorphism group now, two very different flavors. One focus on the topological property, like homological type, homological groups, things like that. Another focus on algebraic property, like establishing normal subgroup, trying to prove this like this group is simple or something like that. Yes. Try to find specific subgroups inside this group, of course groups. So so our focus will be studying the topological of the story. Namely, we want to at least partially understand the homology type of this diffeomorphism. Well, at this point, the fair question is why do we care? Actually, why do we really want to that is so I want to maybe I want to first briefly explain the motivations. Why do we care? For me, there are two reasons at least. Maybe reason number one. Understanding the homology type of this diffeomorphism group help us to classify values of the X functions. So values of matrices. Namely, smooth cycle. Okay. So why is that the case? So let's introduce some more notation. This is a homological group. So we have the classified space. If so it's just defined as you take a contractible space with free action and you take the box. Okay. A specific model of this contractible space can be picked as the space of invariants and the target figures. So here, the boundary means that we should fix a specific conclusion related from the boundary of m to 0 to the boundary inside. And with that, add those things. So there is a characterized version of the way to value theorems saying that as you increase n, the connectivity of this guy will be larger and larger, but then it just becomes contractible, and obviously it has it needs a action of the diffeomorphism group because it can compose the embedding by the diffeomorphism. So this is one specific model, and so to simplify the notation, let me just n text. So for this modular thing. Okay, so most medical tests. So what you will call this?
No buttons.
Okay, that's good. Okay, so why is it legit to call it a vortex? It must classify. So the reason is that if we have a reasonable space, then if B is a CW complex, then starting the homological class from B to its modular space, this will be one to smooth bundle. That's there's a boundary camera transition. So well here let's assume B is a manifold with transition. So by starting the map from, so if you want to, for example, if you want to classify X bundle over a sphere, you just consider homological group this space. And so in particular, for example, M, which is just n-1 if one representative has an orbital class of X bundles for the speed. This is easy to understand because can decompose the sphere into two disks, and only thing interesting is the Gaussian function, the Cauchy function, which is an element in pi-1 of this. And also, we also want to study the homology of this modular space because elements here actually one also find the characteristic classes. Well, so we all have learned characteristic classes for vector bundles. Those are just homological class of B O right? So the linear group, the classified space for the linear group homological class gives characteristic class for vector bundles. And if we want to study manifold bundles, they just form they correspond to homological classes of the classes. So this is one reason. It helps us to understand families. This is reason number one. Reason number two. Reason number two is that this diffeomorphism usually often interacts with geometric structures. On X. So right here, by geometric structure, here I can mean, for example, geometric structures. Data structures. And also for some free manifold, for some full manifold, you can study portraits dimensions. Or Einstein dimensions, and also even smooth. Also, now I can make it longer, hyperbolic structure. Okay, and so the reason is that, for example, if we have a symplectic structure on X, we can just pull back using a diffeomorphism and get another symplectic. Okay. Then this seems like a naive idea, but it turns out this is quite useful perspective. So let me start with talking about some solutions. So now X still a smooth manifold. Let's consider we are going to consider three spaces of vector field. So I know there's F omega S omega. So these are all spaces of symplectic structures. So first, Sx was defined to be just a space of symplectic structure. So the form should be closed. Non-degenerate. Let's take all of the symplectic structures. We can easily equate this as a same model. And what's this guy? Given SK, that's defined to be all symplectic structures in a fixed form class. Here I assume X is closed. Which we can one thing we can do is to fix a cohomology class of the symplectic structure and just study all symplectic structures in field cohomology class. Yeah. And also we have this even smaller space at omega X. This is just defined to be a component of this X omega. Like this. We just take a collective component of this space. So these are three versions of symplectic space of symplectic structures. And there's one very useful. Oh, okay. Well, I also need to introduce function. This is yeah, this is the group of symplectomorphisms. Then this group of diffeomorphisms that preserve the symplectic one. Now we have a fibration. Turns out that there's this fibration. So first of all, if 0 or less, so this means a unit component. Of this. So this maps to S over X. Because you can just pull back F. And it turns out that this is the fibration, and the fiber is just same. And why is this good? Because this allows us to. So that means if we consider the improvement map of symplectomorphism over the diffeomorphism, usually it will fail to be a homological equivalence. Okay. This implies this interesting properties. In other words,
Can you just because of like this intersection? How do I? Are we getting a bunch of components? I mean, this.
so this is these are the symplectomorphisms which are smoothly isomorphic to identity.
Yes, is that the union of components of?
That's a great question. So in many cases, this is not. It is a union of components. Yeah, it is a union.
Yeah.
So we don't take all the components of it, just take part of it.
Yes.
Yeah. It's a union of components of this guy. And we throw away those components which are not even smoothly isomorphic. But usually this guy has more components than this. Well, this is connected. Usually this is not connected.
Yes.
Has a lot. Yeah. We'll see some examples.
Is the topology and the group symplectomorphisms
Yeah, also
this, like this,
yes.
this topology?
Yeah, just stop this. Yeah, and so that means if we find some difference between the topology of this guy and the topology of this guy, we establish some interesting families of symplectic structures of X. And this term, has some concrete applications. For example, I think this exact sequence people sometimes call them complementary exact sequence. Those Farmer first studied in sequence and proved that there exists many, many facts such that I n x I f has on that. Okay. So here basically n is down odd number. So basically it's like roughly speaking, if there exists a homomorphic sphere invalidity X, maybe should use a soft intersection negative k, then one can establish some say, the number of things like they minus under some mild assumptions. So basically, if you have a holomorphic curve with very negative self-intersections, then you can use that. You can use this long-exact sequence together with some Seiberg-Witten theory to detect a non-trivial family of symplectic structures. And this is one thing, and another thing is like this. Also, I think later. So another instance is it is that x is that S2 plus sigma with the genus of sigma greater than 0. Then one can show that this S8 x has infinity many components. For all a square. Okay, so we fix it. One natural question is like we fix a homological class and try to some like symplectic structure in this homological class up to isotopies. And this space has infinitely many components, means that there are infinitely many symplectic structures which are homologous to each other, but not isotopy to each other. Actually, they are all hands on each other by pulling back the standard symplectic structure using an interesting diffeomorphism. By interesting, I mean it's not some diffeomorphism, it's not a product of the structure, it's more into one. It's called Bauer diffeomorphism. And I want you to show that such diffeomorphism cannot be isotoped into symplectomorphism using some geometric curves. And so this is yeah, anyway, so these are some so you can see that by studying the interaction of the morphism book and the morphism book, we get some interesting results about symplectic structures. And also, I want to talk a little bit about smooth structures. Smooth structures. Okay, as Andreas mentioned, it's hopeless. Well, at least it's out of reach now to classify all smooth structures even for manifold. The only thing, I guess, we can do is like to say, okay, there are many smooth structures up to diffeomorphism. So okay, so what I think, so how to study smooth structures, study diffeomorphisms. Here's so we let A be a set of smooth structures. Okay, so now let X be a topological. Just start with a topological manifold. And we let A really should be AX. And let me just write A. A be a set of smooth structures of X modulo diffeomorphisms. Right. So there's a subtlety here, right? Because when we say smooth structure, we mean maximum smooth atoms of that. And but when we say like this manifold has infinitely many smooth structures, any manifold has infinite. Okay. because we can always find two different smooth atoms which are not compatible with each other. That's not so interesting. But when we say a manifold has like more than one smooth structure, we really mean the manifold has more than one smooth structure up to diffeomorphism. So really here we mean A has more than one. Okay. Yeah, but we want to now we can. But if we just want to study smooth structures, not smooth structure after diffeomorphism, what happens? How to approach that question? So yes. So let me consider the group of homeomorphisms. X, this is just the homeomorphisms. X. Look, now we can consider the following map. So we can consider B diff. It's the modular space. Get started. But this X is just now just as a topological manifold with a manifold is smooth structure. Because certainly this group, this space will depend on the smooth structure. Well, at least obvious. It's not obvious at all why this space is. This space should depend on smooth structure, right? So that's just. And we have the obvious forgetful map from B diff to B family. Because any diffeomorphism is just homomorphism.
You're saying what you were just above is actually not so clear. You said A is this set of smooth structures modular diffeomorphisms. Now I don't know what you mean anymore. What do you mean by modular? What are the diffeomorphisms you're running out by?
Any diffeomorphism, orientation preserving diffeomorphisms. Orientation preserving diffeomorphisms.
Oh, yeah, so it's between different smooth structures.
So the original structure was the different groups.
Yeah, but it's comparing different groups and structures. It makes sense.
Okay, yes.
It's a map such that takes the one.
Yeah. If there is a homomorphism that pull back one smooth structure to another smooth structure, then we can get this second element. So for example, for S7, where X is S7, this 8 has 38. Yes. Okay. And now we want to take okay, so we want to take one representative in each equivalent class. Then we can consider this forgetful map. Let me denote this map. Row. Anyway. So this is just forgetful map from the smooth modular space, topological space. Okay. Now we can consider it turns out the following fact, which is not so hard to prove, but I will just state it as a fact. The homotopy fiber of this row, any continuous map, you can turn it into a fibration into the fiber. The homotopy fiber of this row is homotopy equivalent to a space called the space of smooth structures. Okay, this is confusing. What's the difference between this guy and A? Really, I mean, A is a Cauchy space. So here in this space, a point in this space really means a maximal smooth atoms of S. Okay. But there are some points that topology issue. So a better way to define this space is just through simplification set. So basically, by definition, we define a simplification set that this is just a small structure on delta n from X such that the projection is a smooth motion.
Yeah, what's your definition of smooth stuff? It's not the maximal
I mean, the smooth structure of X means an open cover of X.
Like you're not taking a maximum connection.
Maximum, we take the maximum. We take the maximal connections. Of smooth atoms. So, yeah, so you can define this space through simplicial set. The syntax and syntax in this space is just a smooth structure of this product manifold such that the projection map is a smooth subversion. This parameterizes the possible smooth structures of X.
Okay, I think I'm being so, but why is it like not why do you have to closure not like different ones? Like in the definition of things.
Because this is a huge space. Even for example, for S1, let's say, okay, so let's say for R. Okay, so what's R? Okay, so S and R. What's happening?
I see.
It's really just monotone increasing C0 function from R. Is cute. Sorry, monotone increasing and then you need to model out by the let's see, two continuous functions are equivalent if like their composition is smooth. When, for example, when X is R. So this is
And what about A or R?
A of R is just a single point.
But the set you wrote underneath is SMR or zero simplicity?
Let's zero simplices. I mean, well, if we treat it as a simplicial set, these are the zero simplices. And we can also just put a suitable topology of this function space and make it just a topological space.
So pi zero of SMX is not A.
It's not A because it's not A because diffeomorphism doesn't require and this modeling out diffeomorphism is different from taking epsilon. And so yes, so this allows us to so for example, one result of search says that if an element of X is less equal to 3, then rho is always a functional equivalence. Okay, so this is a stronger version of the statement that we usually heard that any 3 manifold has a unique smooth structure. Really, the space of smooth structure is enough. If you think about 3 manifold, 2-dimensional. Okay. But the situation changed drastically in dimension 4. So in dimension 4, one can study, one can compare the topology of this and the topology of homological and get and prove that this is space of small structure is never compatible. for any four manifold, this space has interesting form. Actually, one can actually so one can actually show that, for example, any four manifold pi 2 when x is four sphere, this is assumed to one way. Will prove that the diffeomorphism group of S4 is not homogeneous filtered isomorphic, and one can generalize that result in get this refinement for any four manifold. Okay. So that's the second reason. Start with this time. Yeah. So one can play similar games. Okay, so I play this game for symplectic structures, smooth structures. I feel it's not a good idea to play the other things I did. I would just say you can play similar games. The other structures I mentioned. Hidden structures, positive scalar curvature methods, isometric, hyperbolic structure, all kinds of things. Okay. Anyway, so yeah, so this is the motivation part. Why is it? And now the goal. So the goal of this vector series is to use to understand. At least partially, that's the goal. So I want to say that this is just one approach to study diffeomorphism group on X. There are many other powerful approaches. For example, the result I mentioned just now by Yuki Watanabe will prove that the four-dimensional disk has a non-trivial diffeomorphism group. The diffeomorphism group of a four-dimensional disk is non-contractible. This is proved using the so-called configuration space integral. So that's a different set of techniques. At least for now, it seems like to be perpendicular to gauge theory technique, and that's also very powerful. Still under develop. People are still trying to developing that theory. But I guess since the theme of this lecture is Seiberg-Witten series, so I will focus more on Seiberg-Witten side. I just want to mention that this is not a good. This is just one of the many tools which can be used. Okay, now this finishes the motivation part. I started 9:30, right? So
Yeah.
how long is the lecture?
1 hour.
1 hour. Okay, good. That's great. Okay, so now let's do Seiberg-Witten invariants for families. Okay, so now let's consider a smooth fiber bundle. By smooth fiber bundle, I mean a fiber bundle whose structure group sits inside the diffeomorphism group of X. Okay, and there is a structure group. So there is a particular important case at when the base is another smooth manifold, and this is a smooth fibration if and only if the total space is a smooth manifold, and this is a subversion. Here I assume the fiber is compact, so this is the Kuiper's theory. Okay. For most of the time, I'm just going to assume B is the manifold. Doesn't really matter. Although, in the end, we want to set B to be the classifying space, which is not a finite dimensional manifold. But turns out that usually we just care about like topology up to a certain range. So we can just approach that by a finite dimensional manifold. That's not a too big issue. Okay? So it's safe to just consider a case where E is a manifold. Okay, now for point in the base, I'm just going to set this. We only have the image of I. Then we can consider the vertical tangent bundle. It's just a tangent bundle in a fiber direction. So I'm just going to put TVE. This when the base is another manifold, we can just define it to be the kernel of this one. So it's just a tangent bundle in the vertical direction. Now, when we do gauge theory, what's the first thing to do when we want to do gauge theory? Well, if we have a smooth manifold, we want to do a gauge theory on X. What's the first thing to do? Put a metric on it, right? yeah. That's something unfortunate. Well, unfortunate, because we want to smooth the invariant, but the first step is to put some extra choice. Fortunately, this choice is not too bad. Metric is fine. So so in the family setting, we pick the family metric. I'm just going to use GeoTop which is really a section of BBE. Okay. It's a family metric. Okay. So then structure, then TVE, then this family metric makes the structure group of this vertical tangent bundle into SO4. Okay, so TVE classified a map from E to E. Maybe I expect it right. What's the pixel register?
Yep.
So this so it's not family to which classifies this vertical tangent bundle. And now so the next thing to do is to pick to fix a spin C structure or spin structure on this family. So a spin C structure this number. So okay, so when I write this notation, I mean it's I mean a bundle over B. So sometimes I will just ignore the base and write a single E, which is abuse of notation because E can be. Here I treat E as a family of manifold instead of a single manifold. So a spin C structure, usually I denote as tilde. This is just a lift of this in spin. And also you can talk about a spin structure. I'm also going to use S tilde. It's a lift. So you can further try to lift this to B spin 4. That will give a spin structure.
Should this be B, not B?
Which I mean the bundle is over E,
Oh, the bundle.
right?
B
It's
is the base.
B is the base, right?
Oh,
And we are taking the tangent bundle in the fiber direction, so that's a vector bundle over total space.
yes.
Yeah, and now so it's so just like in the it's not hard to prove that a spinning C structure exists. Then now if W3 of the bundle is 0, and in this case spinning C structure. The set of species structure is a positive over H2 of particles, okay, with the coefficient. And a spin structure exists if and only if the second spin with the path equal to 0. In this case, the set of spin structures is a positive over H1 of this. These are just very similar to the single manifold setting. We're just working in the family setting, and now, okay, so we have set up the spin structure, spin C structure. Now, even for the most of the time, I'm just going to talk about spin C. Okay, given a spin C structure, we have the spinor bundle. As which are as n bundle of E. Okay, we have the Clifford multiplication. I'm going to get S this one. Now I'm going to use SB to denote the restriction of S to the fiber O. And we have the Clifford multiplication map, which is CL. So it goes from this is the algebra of E to S. So this is the Clifford multiplication. Well, these are some. I mean, Tom talked about this algebraic construction. It just works without any difficulty in a family setting. Now, also want a. Now let's fix. Okay. So fix a family base connection. S, well, that's a connection S, which is compatible with the Levi-Civita connection on TBE. Okay, so I'm just denote it by A0 tilde. So usually when I put tilde, I mean the family of them. Okay, really it's just a base spin C connection on each. Okay. Now we can set up. Now, okay, with all these choices, we can set up a Seiberg-Witten map. Okay, so any point in the base, okay, we have the Seiberg-Witten map. It's just I'm going to notify SWB. It goes from S E 0. So, so the map. Fine. Yeah, it's just a Seiberg-Witten map for each file. The formula is just says. But, so here this means the space of spin C connections on this spinor. Okay? So A is a spin C connection, and C is a section of the positive spinor bundle, which just is the FM. Now, really, it's compute the bundle on the AT really means determinant line bundle of this S plus bundle, and minus sigma. Sigma is this quadratic term introduced in this first lecture. First lecture. Well, second lecture. It's the quadratic term. Defined using the Clifford multiplication. And also the operator. Okay. So this is the curvature equation, this is the block equation, and in order to reduce the gauge group to a finite dimensional group, we want to have the fixed condition and the star will be A minus this. Okay. Yeah. So this is Seiberg-Witten map. Okay.
It's a collection of connections over, or it's a collection of like connections over each fiber, or you want to forget some information, right? In the tangential directions so long.
I mean, it's the along the base.
Yeah. Okay.
Yeah, but we don't worry about those. No, it doesn't matter. It doesn't matter. Yeah. We just care about the connection. We just care about the. Oh, okay. That's right. So a family-based spin C connection on S is really not a connection on S. It's just you just care about the covariant derivative in the fiber direction. You don't care about the covariant derivative in the base direction. Okay. Yes. Okay, so we have this Seiberg-Witten map. Then in order to get a nice moduli space, we need a perturbation form. So okay. So eta tilde is a section. In other words, on each fiber we have a yeah. So on each fiber we have an imaginary value of the self-diffusion. Okay. So I also write it as a connection of eta B for each B. Okay. Now, the thing we're interested in is the Seiberg-Witten moduli space. And yes, W. Okay, so here I'm putting the family species structure and the metric and also the facial form, okay, is defined to be the space of tuples B, A, C Okay, where B is a point in the base, A is spin C connection on SB, and C is the spin fiber, such that SWB you see equals what? Equals delta B 0, 0. In other words, we use this eta to curve the curvature equation. This is the Seiberg-Witten moduli space. Okay. And oh, sorry, let me put a GeoTop here. And with that, so this moduli space has a gauge action. Gauge action. S1. So EI theta just add cubically on the first two components and add this scalar multiplication. Third component. Okay, this equation is preserved under this U1 symmetry, or maybe it's better to say U1. Okay, and we just define M as W, as Furuta, Furuta, this moduli space quotient by U1. Okay, so here U1 really is the constant gauge transformation. Okay, so this is the moduli space we're interested in, but now we want to say that for a good choice of G and eta, this is a manifold, and one can extract the family Seiberg-Witten invariant from this manifold. Okay, so that's what we are going to do next. As maybe in the last 2 minutes, let me introduce some other bundle which will be useful. Okay, associated to this smooth fiber bundle. Oh, sorry, I forgot one important assumption here. Let's still assume E1 equals 0 to make our life easier. Okay, yeah, anyway. So, okay, now let's consider we have a given a smooth fiber bundle E over D, we can consider the associated bundle for H2EB, whose fibers are just H2 of the fiber. Let's take root. Okay. So this is a flat one. Because it really is, you can use the coefficient. Yeah, and form another bundle that give a canonical flat reaction on this bundle. Okay, and each fiber flat. Each fiber can use. Which is just the sexual form of X. Now we can consider a sub bundle for H2 plus of E or B. Okay, so this is just H2 plus of X, the space of homology. So we can put the space of harmonic full forms on each fiber and form a smaller vector one. So the rank of this guy is the rank of this guy is B2. The rank of this guy is B2 plus. Okay, so this is a subform.
But it will no longer be flat, right?
Oh, what?
It will no longer be flat.
It no longer be flat, but it's not flat. No way. And it's actually it's a maximal positive definite subform of this graph. And yeah, And I just want to say that this bundle, H plus bundle, it depends on the choice of GeoTop, because you need to use Hodgson operator to define H plus. But up to given any two choices of matrices, these bundles are isomorphic. They are isomorphic, and isomorphism is canonical up to homological. Okay, so the fact is that given any vector bundle with a bilinear form, the space of the maximal positive subbundle is compact. So there's a integral choice of this H plus, which can be induced from the contactable choice of mesh. Yeah. So I think that's the end of lecture 1. The second lecture we are going to use this bundle to say something about the moduli space and then to extract the very Seiberg-Witten invariant and then the multiple time invariant and start talking about applications.